Welcome everyone. My name is Simon and I'm application specialist for X-ray diffraction at the Thermo Fisher Scientific. First, I want to give you a short overview of the agenda of this webinar. Beginning, I will give a short introduction into our X-ray products portfolio and in the technique itself. Afterwards, I will directly go to some applications which could be of interest for you. First application will be covering thin films. There will be a slide part with X-ray fluorescence spectroscopy also in this section. Afterwards, I will show you some measurements in transmission and reflection mode. Then we have an heating experiment of rubidium nitrate. And last but not least, there will be a section about Laue diffraction. In this section, I will give you also a brief introduction into the technique. So now we start right away with a short introduction. We have a look on the spectrum of electromagnetic radiation. On the very left side, on the low energy side, you can see visible light, which you know everyone can see, and it enables us to see such beautiful pictures as this one, which was taken in Switzerland close to our factory. The high energy side on the far right, we have gamma rays, which are mostly produced by stellar objects like this black hole. Between those two, we have X-rays. There are soft X-rays and hard X-rays. The X-rays which are mostly used for diffraction are on the hard X-ray regime. On the bottom, you can see some commonly used radiation types in X-ray diffraction, starting from chromium on the low energy side, moving on to silver on the high energy side. At Thermo Fisher do not only offer X-ray diffraction, but a huge number of other techniques closely related to materials and structural analysis. We can offer solutions for structure analysis like electron microscopes, SPM, and XRD. We have even a bigger number of instruments which can help you distinguish the composition of materials, like mass spectroscopy, EDX. There is also XRF. We have XPS, Raman, FTIR, and some combined techniques. And we can also investigate the properties of materials like particle size, thermal properties, and rheological parameters. We now have a closer look on our portfolio of elemental analysis. We have Spark OES, which is mostly used in metals industry, also combined with automation. We have a range of X-ray fluorescence instruments, energy dispersive ones, and also wavelength dispersive ones. And we have, on the other side, standalone powder X-ray diffractometers and also a Laue diffractometer, which you can see here. And between those two groups, we have one instrument which has integrated XRF and XRD capabilities. So in our XRD portfolio, we can not only offer benchtop instruments, which you can see here, also more advanced configurations. On the top side, you can see our Laue diffractometer, which I will go into more details later, and also a 4-circle goniometer. So basically, we are offering XRD for everyone. To give you a brief overview of X-ray diffraction and the different fields of applications. On the left side, there are techniques which are related to single crystals, standard single crystal X-ray diffraction, and also Laue diffraction. I'm only covering Laue diffraction today, no single crystal diffraction. And on the other side, there are techniques which are more powder related, like high resolution XRD, micro diffraction, and what is classical powder or polycrystalline XRD. So today we will talk about these two topics, and the other ones are maybe not. So what is X-ray diffraction? I know that there are some people in this call which are maybe bigger experts than I am, but I want to try to give a brief introduction to everyone. So maybe you remember your physics class in school or maybe in university. There is an experiment where you do diffraction of a laser beam at a slit or grating. And behind this grating, you get a diffraction pattern, which consists of minima and maxima. And from these, you can get some information of the slit size of the grating. If we now go to more energetic radiation with smaller wavelengths, can reduce the size of the grating, which acts as a diffractant. And in case of X-rays, we are going down to the regime of atoms. You now think of a three-dimensional periodically ordered arrangement of atoms. Atoms will form, if they are periodically ordered, they will form something which is called lattice planes. So there are planes and they repeat itself in all dimensions. And the distance between these planes forms something like a grating. At this grating, we can do diffraction, and the position of the signals we get from our diffraction experiment is due to, which you can see here. So that's the most fundamental equation of X-ray diffraction. And this d value here is the distance between these atomic planes. You can also see it here. It really depends on which type of material you are investigating. So what we are mostly doing is powder diffraction. So what is a powder? Powder contains a large number of grains which are probed by X-rays. These grains are small according to the beam size, but they don't have to be too small because then you get other effects. Each of the grains which is in black condition will diffract according to its orientation. So we get several diffracted beams for a fixed sample orientation. So these diffracted beams form something which looks like a cone, and they are called the bicones. So here you can see what I'm talking about. So you have crystallits, and all of these crystallits have different orientation, and you get diffraction in different directions according to the orientation of these crystalloids. And as a take-home message, a powder is an infinite number of crystals randomly orientated in space. So our setup is quite unique. We are using a big band detector. It's called a CPS, Curved Position Sensitive Detector. A gas discharge detector with a delay line. And it has a radius. And in the center of this radius, we place our sample. And on the other side, we have our source. You can see it here. And we choose one fixed incidence angle at the beginning of the measurement, and then just expose the sample to X-rays, and we get these signals, the bicones, and they intersect with our detector and are measured. And upon measuring them, we just count the peaks, the intensities, the photons, and then you get a diffraction pattern which looks like this. So this is silicon measured for 60 seconds, 1 minute. And you can see that this is a very nice diffraction pattern, even after 1 minute of exposure. To give you a brief overview of our capabilities in benchtop instruments, there are two we can offer. On the one side, there is the Equinox 100, which is a very compact benchtop instrument with a micro focus X-ray source to X-ray mirror optics. The type of radiation we have available is cobalt, copper, and the molybdenum. The advantage of this instrument is that it's lightweight and easy to run and maintain. It has high flux and a low total power consumption. This means you could also run it using a battery or a generator, even in field. It requires no external water chilling, and it is a very rugged, student-safe design. So we have one instrument installed at LMU Munich, and it's solely used for teaching purposes, where students measure their own samples in internships. And the instrument is still running, no realignment necessary. So this instrument is really student safe. They are not able to break it. So this is really an easy to use XRD for everyone. On the other side, we have a Equinox 1000, which is a full-size instrument made compact. It has a 3 kilowatt generator with no power limitations. We can apply a germanium 111 monochromator. It uses a standard seal tube, and it's maybe the most convenient way to bring some brilliance to your bench. We have plenty of sample holders available for different applications. And the nice thing is that you can just choose your application and measure right away without any realignment, just by changing the sample holder. One for reflection and transmission measurements of flat samples. We can also measure capillaries, which is quite unique. We have different sample changes with different positions. We have an omega Z stage for grazing incidence and reflectometry measurements, and we also have in-situ chambers for heating experiments up to 500 degrees centigrade. I will do as I will show a little bit of X-ray fluorescence spectroscopy. I just want to give you a brief reminder how this technique works, because it's different to X-ray diffraction. With X-ray fluorescence spectroscopy, we excite an atom using X-rays, and the atom is ionized. Afterwards, it relaxes and fills the hole. And upon filling the hole, it emits radiation X-rays with a specific energy depending on the positions of the electrons. Afterwards, these X-rays are detected, and from the energy we can recalculate the element they are originating from. So we can get elemental composition of mixtures of any type of material. And this technique can be used for surface and layer analysis. Surface is a surface analysis technique, so the penetration depth really depends on the energy and the sample composition. So it's, for example, 30 micrometers for palladium X-rays in palladium, but only 1 micrometer for aluminum X-rays in gold, for example. If we want to do layer analysis, it will heavily depend on the sample structure, on the thickness and composition of the layers. We need one unique element per layer to, for example, determine the thickness, on the number of layers, and also on the substrate. Give you some idea about the thicknesses. We have a linear and not any more linear range, but one we can, which we can refine using fundamental parameters. From about 0.1 micrometer to something like 7 or 8 micrometer, where we can easily do thickness analysis. And afterwards, we are getting in the regime of bulk analysis, where it's not longer possible to do thickness analysis. So now we start with our first application in thin films. We want to measure thin films with very small layer thicknesses. we have to somehow increase our measurement volume to get reasonable measurement times. To do so, we do something which is called grazing incidence, where we use a very small grazing angle, like a 0.5 or 1 degree, and let the beam graze over the sample to increase the measured volume. In this case, we did this with samples, it's solar cells. And here is a series of measurements. Each measurement is only 2 minutes, so it's quite quick. Starting from 0.5 up to 5 degrees omega, so that's the incidence angle. And you can see that at low angles like 0.5 and 1, we have only one set of signals. And at 1.5, we get an additional signal here, which then increases in intensity. So we have two layers, which we can separate by the incidence angle. We afterwards have a look up which phases these signals belong to by comparing it to a database. We find two phases. One is copper gallium indium selenide and the other one is molybdenum. So this is a CIGS solar cell, and it uses molybdenum as a back electrode and copper gallium indium selenide as the absorber material. So we can nicely see that we can get signals from both of these layers, and we can also measure the layer thickness using, in this case, our benchtop EDXRF machine. Molybdenum, we get 0.34 micrometer thickness of the layer, which is nicely in the range of this type of material. And for the absorber layer, CIGS, we get 1.43, which is also a quite common number. So it looks very nice and it's quite convenient to use this method. A more advanced application in this field was done by one of our customers from the Austrian Institute of Technology in Vienna. They are doing research on solar cells. And in this example, they were doing substitution in zinc oxide with magnesium, deposited by spray pyrolysis. So this material is a potential substitute for cadmium selenide in CIGS solar cells, because cadmium selenide is quite toxic, so it's nice to have something which is less toxic and even less costly. If we first have a look on cross-sections of the layers which were produced by the spray pyrolysis with varying magnesium content in the solution, you can see that with no magnesium, we have a very dense, nice layer. And upon increasing the molybdenum content, we get nanowatt growth on top of the dense layer, which increases with increasing magnesium content. So if we now do X-ray diffraction on these samples to see what's going on structurally, we see that for pure zinc oxide, we get a diffraction pattern, and upon increasing the magnesium content, the first look, nothing changes too much, but at some point we get additional signals, and these belong to a periclase type structure. So the first patterns are a zincite type structure, and then we get a periclase type structure. What we can also see is that we have preferred orientation of the zincite structure type of 0001. And no competitive growth, so it's only this preferred orientation. And the periclase type structure has another preferred orientation. If we now try to figure out if we have a substitution of magnesium, we can have a look on the lattice parameter, so on the position of our reflections, and we will see that they will shift with increasing magnesium content, which means that we have magnesium uptake of the zincite type structure up to a certain degree, and afterwards we get another phase. If we now also do not only investigate the magnesium concentration in our solutions, but also vary the other variables like the zinc acetate or the acetic acid concentrations, you can see that it only affects our preferred orientation. So the preferred orientation changes, so the texturing and the thickness, but the magnesium content, as you can see here, is really only controlled by the magnesium concentration in our solutions and not the other properties. The last step, the group posited one selected composition, which you can see here, on commercially available substrates like indium tin oxide or fluorine-doped tin oxide. See if it influences the orientation of and also the growth. But in this diffraction potence, you can see that there is very little influence on the orientation coming from the substrate for both substrates. And the purpose of this study was to control of the band gap of this material, and by varying the magnesium content, you can vary the band gap between 3.28 and 3.5 electron volts. A last application in this application field is X-ray reflectometry. That's not diffraction, but reflectometry, where you measure the interference of the reflected beam. Do not get structural information as for X-ray diffraction, but you can get some physical parameters out of the scan, which you can see here, like the density of each layers and the thickness of the layers and also the roughness. This method even works with hundreds of stacks of layers, and the only precondition is that the layers have to be quite thin, something like 100 nanometer, and the sample has to be absolutely perfect. But then it works also for crystalline and amorphous materials. So there is no limitation for crystalline materials for this technique. The application is in-situ measurements. Oh, sorry, it's a transmission and reflection measurements. And I will show you an example of tenofovir, which is an anti-HIV drug. First, with our benchtop instruments, it's easy to change between reflection and transmission, as you can see here. So this is a transmission mode, both with the same sample holder, where you can measure flat samples with a polymer foil. And this is done for transparent samples and to get an increased resolution. On the other side, you can see the reflection mode. It's just a shift of the sample holder by 90 degrees. And this one works with flat samples. We have front and rear filling sample holders. It works for any sample, and you have an increased intensity compared to transmission. This is how it looks in the instrument. So you can see it's quite narrow space, but it works nicely, and it's really easy to change between those types. Now the example. So this is tenofovir measured in 5 minutes measurement time, so quite quick measurement. The green is transmission and black is reflection. So what we can see in the first view is that they do not look similar. And this is due to preferred orientation. So if you, due to sample preparation, the crystallites orientate in a specific orientation, and so the intensities we get from the signal are somehow affected by these. These blue tick marks are the entry from the database, so you can see that in the reflection scan some signals are missing. And so, for example, here in the reflection scan we only get one signal. we get at least 2 in transmission. So we can increase the resolution doing so. We are coming to the in-situ application on the example of rubidium nitrate. Rubidium nitrate is a nice reference material because it has plenty of phase transitions at quite low temperatures. The setup looks like this. So we have this little heating chamber. It's from Anton Paar. It's called BTS 500, can heat from room temperature up to 500 degrees centigrade. We're using a copper source and a nickel sample cup. And we are using a measurement program where we do 72 measurements of 2 minutes every 4 degrees centigrade. And this one, the experimental time is something like 2.5 hours. So it's quite quick and quite convenient to do. The result looks like this. So this is a Gougne plot of all of our experiments from room temperature up to something like 320 degrees centigrade. And you can see certain changes. So here at 177, there is a change. So here is the first phase transition. Here we get reflections, so additional reflections which appear. So here is our second phase transition at 313 degree. We have the last phase transition. And above that, the sample decomposes. So it's not longer stable and we get some amorphous signal, which shows us that the sample decomposed. Now we are coming to our last application, which is Laue diffraction. So I put it at the end because it's different to all of the other applications. First, to give you a brief introduction, this technique is used basically only with single crystals or with wafers. It uses white radiation with the molybdenum or tungsten targets usually. Each of the lattice planes of our single crystal will diffract X-rays with wavelengths that satisfy Bragg conditions. So this means our diffraction pattern, which looks like this, you get this nice spots here. It looks like the night sky. But not all of these signals are coming from the same wavelengths, but they are coming from different wavelengths. So this is very different to powder diffraction. This can be used to determine the orientation of single crystals. This technique is very difficult to do a structure solution of unknown crystals. So it's basically only usable if you already know the crystalline structure of your material. But it has quite good time resolution because you get a lot of information in a short time. So it's also possible to use it for in-situ applications, which is mostly done with synchrotrons, but it's also maybe possible in a lab. There are two different setups. The first setup is back reflection, where you have your source on the opposite side of the detector with a hole in the detector, and then you measure the back reflected signals. Also possible to measure in transmission mode, where you just shoot through your crystal and you measure on the opposite side on your detector, you measure the signals. So that's similar to classical single crystal diffraction. But our instrument is a back reflection instrument. We don't have transmission Laue instruments. The instrument looks like this. So it's a floor standing instrument. It has a 3 kilowatt generator, as I mentioned, molybdenum or tungsten sources. We have a set of different collimators. We are using a CCD camera, which you can see down here. This little hole in the center for the beam. We have a goniometer head on the XYZ stage. We are also offering customized sample holders on request. The whole instrument is computer controlled, and we have a video microscope for sample alignment. And this instrument is maybe a convenient way to bring some orientation to your lab. So the CCD camera is quite big, has 18-bit dynamic range, and we are using automated background subtraction. Here you can see a schematic of the sample holder. So it's It's equipped with a well diamond goniometer. So it's usable with a wire saw if you want to cut you correctly. Our first experiment is on a single crystal of silicon, which we rotate along the phi axis in 90-degree steps. So here is 0 degree, where you only can see the 111 plane of this crystal. And it's the same in the 180-degree position. On the 90 and 270-degree positions, you can see that also other reflections which are due to other planes appear. So this means there is a misalignment. It's not perfectly aligned in the 111 direction of the silicon crystalline structure. So you can see acquisition time is 20 seconds. So this method is really quick. Another example I want to show is a quartz resonator. So this is a very commonly used electronic part like this. If you open this, you will find something like this. The quartz resonator vibrates along a crystallographic axis if you apply an oscillating voltage. So you can use it, for example, in watches or several other applications. And this is an actual picture from our video microscope. So you can see we can do some spotting mapping. And after exposure, you get your Laue diffraction pattern of this small spot here. So you can really also scan a crystal. Last example I want to show is on fluoride material, lithium yttrium fluoride, which is used for solid-state lasers. To produce the lasers, you have to cut a single crystal in a specific orientation, and to align it, you can use Laue diffraction. So we adjusting the tilt in each direction till we reach the 111 orientation. So you have to do it in each direction, and afterwards you can directly transfer the goniometer to a wire saw and cut the crystal. You, for example, want to detect crystal defects. So if the growth of this single crystal has not been perfect, you would see something like this. You would see one set of reflections in one orientation, looks quite nice, and on rotation, then you get a separate set of reflections. So this means that there is some misgrowth or some twinning or some defects in the crystal, which shows you that you maybe should not use this crystal for your application. So that's it so far. I want to thank you for your attention, and you can always visit us on our webpage, which you can see here. And now we can open the question and answer discussion session. Thank you.
Thank you very much, Simon. We have now come to the Q&A section of today's session. Please make use of the chat or Q&A box to continue asking your questions. Simon, our first question for today is, what is the advantage of a monochromator?
So you always have to somehow, or it's somehow shape your beam. So in classical Bragg-Brentano instruments, usually you use a filter to get rid of the K-beta radiation, because each of the energies in your radiation will yield a signal. So if you, for example, have K-alpha and K-beta radiation, you get 3 different set of signals, which will make it tough to evaluate the data, even if there are many reflections. So you want to reduce this number. You can use a filter, but then you get artifacts of the absorption edges of the material which is used as a filter, and you reduce the intensity. And so you can also use monochromators or mirrors. Monochromators use diffraction because the diffraction angle of each energy is different. So you can, for example, separate K-alpha 1 and K-alpha 2 and K-beta by using a germanium monochromator, and you can even focus the radiation to get more intensity. Then you get very brilliant radiation, which only consists of one energy and only one set of signals. But you sacrifice some intensity. Mirrors, on the other side, use the total reflection of the X-rays, using the same principle as monochromators by using the different total reflection angle, which also depends on the wavelengths. And this allows you to separate K-alpha from K-beta radiation, for example, but you get high flux. So you have two sets of reflections left, K-alpha 1 and 2, but you have a very high flux, so high intensities and shorter measurements times.
Simon, the next question is in two parts. The question is, are there any advantages of XRD instruments for asbestos analysis? How can we analyze asbestos in cosmetic samples using XRD?
So as far as I know, there are some norms which apply for asbestos in cosmetic industry. So not very familiar with these norms, but in principle, you get, so the asbestos is a crystalline material, so it's a silicate, and it will give some signals, and which then could be quantified. There is always a limit of detection, and this very specifically is different for each sample. So in principle, the best thing is to just do test measurements and see if we can satisfy the need with our instruments. But in principle, something like this is possible.
Simon, next question we have is, could you explain the reason of splitting the diffraction plane 220 and 331 for magamite?
So I would like to answer this question maybe after the seminar in an email, because I think this would be is too much for this format right now, and maybe I have to look in some book or some publication. So I'll talk.
Thank you, Simon. Next question we have is, which method is more beneficial, Laue or powder diffraction?
Really is up to your application. So you cannot do the same with both methods. So if you want to do orientation with powder diffraction on single crystals, it just will not work. So it really depends what you want to do. If your problem is that you're having, I don't know, mineralogical samples and you want to know the phase composition, then Laue diffraction will be of absolutely no help. You have to do powder diffraction. If you want to orientate a crystal to cut it in the right direction for some experiments like, I don't know, some exotic magnetic properties or whatever, then Laue diffraction will be very helpful and it will help you to get your job done, and powder diffraction will be of absolutely no help. So it really absolutely depends on the application.
Simon, the next question we have is, can we measure phase changes of refractory bricks as a function of temperature?
Yes, in principle, yes. It depends on the temperature range. So with the bench tops, we are limited to 500 degrees centigrade because of the chamber, but we also have a series of floor standing instruments. And on these floor standing instruments, we have a broader range of heating chambers where we can reach up to, I think, 2,200 degrees centigrade. So depending on the temperature range which you want to measure, you have to choose the instrument and the chamber, which allows you to reach this temperature range. But then it's possible, no problem.
Simon, next question is that if we increase exposure time, does it affect the XRD pattern?
Yes, it does. So there is a function which affects the signal to noise ratio. So if you want to double your signal to noise ratio, you have to increase the measurement time by 4. So there is a square in it. And signal to noise ratio is just you get your noise band, which is maybe something like 100 counts, and you have a signal of maybe 1000 counts. So the signal to noise ratio is, in this case, it's 10. And so this is also this is known as the counting statistics of your scan. So usually you have to choose a measurement time which yields the signal to noise ratio which you need to solve your problem. And by increasing the measurement time, you can also get a better signal to noise ratio.
Thank you, Simon. Next question is related to sampling methodology. The question is that by crushing the sample, is there any change in measurement?
It depends on the sample and on how you crush it. So, for example, if you use an agate mortar, and if you are very careful, you can usually crush any sample. Some samples are very sensitive for heat or for pressure, and you will change them. But then you can try to measure them as is, but sometimes this will yield not that nice diffraction patterns. But then you have to live with them because there is no solution. And you also have to be careful with ball milling, because upon ball milling you apply a lot of heat and pressure, and you could change the sample. So really depends on the sample, and you have to be careful.
Thank you, Simon. Next question we have is it possible to measure and characterize in liquid crystals?
In principle, yes. It depends on which range of 2 theta angles are necessary to be reached, because we are not offering SACs, so small angle X-ray scattering instruments. So our measurement range is, depending on the instrument, limited to something like maybe 0.5 degrees theta, 2 theta. So if it's sufficient to measure, let's say 0.5 degrees 2 theta and upwards, then there is something we can offer. If it's necessary to measure below that, then we don't have a solution at the moment. We don't have SACs instruments.
Thank you, Simon. Our last question for today seems to be related, but you can probably throw more light on that. Are we able to perform low angle measurements at less than 10 degrees using XRD?
Yes, of course. So as I mentioned, there are specific SACs instruments where you can measure down to, I don't know, maybe 0.1 or even below 0.1 degree 2 theta. What we can do is, depending on the setup, we can measure down to something like 0.5 degree with a big floor standing instrument, and the bench tops can reach something like 1.5 degree 2 theta.
Thank you very much, Simon. Ladies and gentlemen, that's all the questions we have time for today. We will follow up by email to all participants on the questions we were unable to cover. Very warm thanks to Simon.
Ankush, Ravi here.
Yes.
Just wanted to,
yes, Ravi.
Just because we have a few minutes time left, so I just wanted to make some conclusive remarks and some key takeaways for the benefit of everybody in this call. Yeah, just 1 minute quick. So from what Dr. Simon Wells-Miller presented today, there are 3 takeaways that I would like to conclude with. The first one is that thanks to the unique technology that we have in our Equinox XRD systems, mainly the detector technology, even on the bench tops, they're extremely rapid, very easy to use, fast acquisition times for a variety of materials and applications, as Simon has walked us through various applications. This means that if you're a research scientist in a laboratory dealing with the materials and looking at their properties, the physicochemical properties, any time-dependent structural variations, structural phase transitions, properties of alignment, preferred orientations, crystallite variations, anything that is impacting a structure of a material as a function of temperature or a function of any external parameter, can be measured in real time, extremely rapidly, almost in situ as the transitions happen. This is one of the most important applications of this type of technology, this type of products. So kinetic studies, reactivity studies, crystalline formulations, if you're in pharmaceuticals or if you're doing synthetic chemistry, you could take advantage of this technology to monitor how the crystallization is happening as a function of time by scanning the sample literally in few seconds, every 5 seconds to 10 seconds. So all the chemistry labs, inorganic, applied, physical, metallurgical, material science laboratory scientists could take advantage of the real-time simultaneous XRD system that Simon presented to study the kinetics, reactivity, and all the time-dependent phenomena. I think that's one of the biggest advantages of this. The second is for the teaching labs, those students who are going to work with diffraction on variety of materials for teaching purposes, for learning X-ray diffraction, for data processing of variety of materials. It's a convenient, easy to use instrument that Simon has walked us through. As you saw the architecture and technology of the instrument, they are designed to be used for a variety of materials with a variety of accessories, thin films, small quantities of powders, granulates, and any bulk material very quickly introduced into the system and measured within few minutes, which is very big advantage if you have a class of 20 students and you would like to take advantage of one sample to be done by each student. You have 20 times 5 minutes. That's about the maximum time that a student would be spending on the instrument. So the cross section of student interaction for X-ray diffraction on this type of technology is extremely efficient for a professor to walk through variety of applications in a teaching laboratory. And the last key takeaway is that these are very affordable instruments. The running cost or operational cost or the accessories are designed such a way that financially, these are not instruments that would consume huge amount of budget in a laboratory. As you know, that X-ray diffraction is a complementary technique to a variety of other spectroscopy tools in the same laboratory. So very often, your budgets are competing for different techniques for material science. And so it's also very important to see that when we emphasize so much on the benchtop instruments that Simon presented today, it is also to make them economically viable for majority of the laboratories alongside an FTIR or a Raman or a small benchtop EDXR type instruments. So that's also very important that there is no single technique that gives the absolute truth. It's always a combination of multiple techniques that material characterization is made complete. So those are the three key takeaways: fast acquisition, kinetic reactivity studies for materials, excellent tool for teaching X-ray diffraction at all levels, and very economic budget within the laboratory space and the scope. So those are the three key takeaways I wanted to emphasize. Ankush, thank you very much.
Thank you very much, Ravi. And thank you, Simon, for conducting this session. Ladies and gentlemen, this brings us to the end of today's webinar, and we hope to see you again for future sessions. Our sincere thanks for the high levels of participation. Goodbye for now. The phone lines will be closed. Thank you so much.
Thank you very much for joining us today in our webinar on XRD in academia and research. We will be sending out a link so you are able to download the pre-recorded session, including the Q&A. If anyone has any other needs, requests, or questions, please reach out to your local Thermo representative and we'd be happy to help you. Again, thank you for joining us, and we hope that you learned something today. Have a good day.